Let's solve another thermodynamic problem involving a closed system. And this time, let's apply our energy balance to a sequence of processes that form a cycle. So a gas undergoes a cycle in a piston cylinder assembly consisting of the following three processes. Process 1, 2. It's a constant pressure process where P1 is 1.4 bar, V1 is 0.028 cubic meters, and the work done in process 1, 2 is 10.5 kilojoules. Process 2, 3. It's compression with PV equals constant and U3 equals U2. Process 3, 1. It's a constant volume process where U1 minus U3 equals minus 26.4 kilojoules. There are no significant changes in kinetic or potential energy. Sketch the cycle on a PV diagram and calculate the net work for the cycle in kilojoules. Calculate the heat transfer for process 1, 2 in kilojoules. Let's lay out our storyboard. We have a piston cylinder assembly, and we've defined the system with this dotted line to be the gas inside the piston cylinder. If heat transfers energy into the system, that's regarded as positive heat transfer, and an expansion of the gas pushing the piston into the surrounding area is regarded as positive work. Let's write down all of the given data that we know at this point. We know that there are three states and three processes in this cycle. We know the pressure and volume of state 1. We don't know either in state 2 or state 3. But we do know that process 1, 2 is a constant pressure process. That process 2, 3 is a polytropic process with PV equals constant. That is to say, the value of N is equal to 1. And in process 3, 1, we have a constant volume process. We also know the work done by process 1, 2 is 10.5 kilojoules. We know that U3 is equal to U2. That's the internal energy of the gas at that state. And U1 minus U3 is minus 26.4 kilojoules. Now let's draw a property diagram, a PV diagram, to visualize this process. We know that the pressure at state 1 is 1.4 bar, and the volume at point 1 is 0.028 cubic meters. Okay. We know that process 1, 2 is a constant pressure process, so it's going to lie on a horizontal line on this PV diagram, and it's going to take us to state 2. We don't know the volume, but we know that the pressure at state 2 is 1.4 because of the constant pressure process. Now, the second process is a polytropic process with N equals 1. That's going to show as a concave line going upward from state 2 to state 3. And it will go up to some unknown pressure, P3. But because it's a cycle, and because we have the third process is constant volume, that must take us back to state 1. So that we know that state 3 must have a volume of 0.028 cubic meters. And finally, process 3, 1 is a constant volume process. So it's a vertical line on a PV diagram. And to become a cycle, state 3 has to take us back. This process must take us back to state 1. So this is what we know, and this is what we don't know. We don't know P3, okay, and we don't know V2, but we do know this process 2, 3 follows the equation that PV is equal to a constant. We're going to model this as a closed system. We're going to assume there's no changes in kinetic or potential energy, and we know that the three processes form a cycle. And what we want to find is, first of all, the net work of the cycle in kilojoules. And secondly, the heat transfer during process 1, 2. So using the expression for work for constant volume process, or excuse me, a constant pressure process, we know that the work done by a constant pressure process is the pressure times the final volume minus the initial volume. All right. We can rearrange this equation and solve for V2 because that is the unknown we wish to find. It's simply V1 plus work for the process 1, 2 divided by the pressure for process 1, 2. Well, all of these values are known. The initial volume is 0.028 cubic meters. The work is 10.5 kilojoules, and the pressure is 1.4 bar. We do need to convert the second term. We have to convert 100 kilojoules is equivalent to 1 bar cubic meter. This gives us a volume at state 2 of 0.103 cubic meters. Now, we want to find the work done by the cycle. Well, the work done by the cycle is the work done by each of the processes added together. It's the sum of the work for each of the 3 processes. Okay, and we know the work for process 1, 2, that was given as 10.5 kilojoules. So we need to find the work for process 2, 3, which is this polytropic process. And previously we have solved the integral for work of a polytropic process, in this case with the value of n equals 1. And we found it to be the pressure times the volume at the beginning of the process times the natural log of the final volume over the initial volume. So we can plug in values for all of these variables. We know that P2 is 1.4 bar, V2 is 0.103 cubic meters, and then we take the natural log of V3, 0.028 cubic meters, divided by V2, 0.103 cubic meters. We convert bar cubic meters to kilojoules, and we have work for process 2, 3 is minus 18.78 kilojoules. And finally, we must calculate the work for process 3, 1, but because it's a constant volume process, we know that without a change in volume, no work can be done. So work for process 3, 1 is 0. So we're going to add all these together to get the work for the cycle. The work for process 1, 2 was 10.5 kilojoules. The work for process 2, 3 was minus 18.78 kilojoules. And work for process 3, 1 was 0. So the work for the cycle is minus 8.28 kilojoules. So we can use an energy balance now to find the heat transfer for process 1, 2. We know that delta U for process 1, 2 is equal Q for 1, 2 minus work for 1, 2. We can rearrange and expand this. We'll say that the heat transfer for process 1, 2 is equal to the internal energy at state 2 minus the internal energy at state 1 plus the work done by the process. But we know that U3 is equal U2, so we can substitute that. And therefore, we get Q12 is U3 minus U1 plus work 1, 2. We were also given that U1 minus U3 is minus 26.4 kilojoules. Well, this implies that U3 minus U1 is going to be a positive 26.4 kilojoules. We can now substitute these values and solve. Q for process 1, 2 is equal to U3 minus U1, which is 26.4 kilojoules. And then we add the work term. The work done by process 1, 2 is 10.5 kilojoules. So we get the heat transferred in process 1, 2 is 36.9 kilojoules.